Welcome everybody to today's robotics seminar series presentation sponsored by Lockheed Martin. Today we have the great pleasure of receiving Rahul Mangharam, associate professor in electrical and systems engineering at the University of Pennsylvania. To tell you a little bit about Rahul's background, he built safe and autonomous systems at the intersection of formal methods, machine learning, and controls. He applies his work to safety critical autonomous vehicles, urban air mobility, life-critical medical devices, AOT for agriculture, and AI co-designers for complex systems. He's the Penn Director for the Department of Transportation's $14 million Mobility 21 National University Transportation Center, which focuses on technology for safe and efficient movement of people and goods. Rahul received the 2016 US Presidential Early Career Award from President Obama for his work on life-critical systems. He also received the 2016 Department's Energy's Clean Tech Prize Regional Award, and the 2014 IEEE Benjamin Franklin Key Award, the 2013 NSF Career Award, and the 2012 Intel Early Faculty Career Award. And he was selected to be in the National Academy of Engineering for the 2012 and 2017 US Frontiers of Engineering. He has won several ACM and IEEE Best Paper Awards in cyber physical systems, controls, machine learning, and education. And with that, Rahul, I'll let you take the floor and introduce your work.
Sure. Thank you so much. It's such a pleasure. Even though it's remote, we'll make this a very exciting talk for you guys. I don't have to do much because the topic itself is super exciting, and it's all about our adventures and our research in autonomous racing. So things are moving fast, things are crashing, but at the end of the day, the question is, what can we learn, and more like what can you learn from our experiences in autonomous racing that you can incorporate in your research and in your course projects. So just to begin from the top, my research is on life critical systems and safety critical systems. And in order to build such systems which have software enabling this different levels of autonomy, different levels of decision making, we have to incorporate mathematical models of a certain type where we can then evaluate that under all possible interactions, no matter what is in the environment, that this system will not behave in an adverse manner. And so we developed the models that are formally verifiable, and we use formal methods to develop such models. And the research always involves some type of control systems that are where we have this sense plan actuate loop as part of it. And under the hood, almost all our tools have some kind of learning component. It's not necessarily applied machine learning, but it is machine learning, as you will see, in terms of exploring certain solution pathways. And we apply this research, in the areas of implantable medical devices for cardiac systems. So these are like implantable pacemakers, defibrillators, or surgical guidance systems. Don't worry, I won't talk about any of that bloody stuff over there, but those are also autonomous systems that are implanted in your body. They are deciding whether to shock your body or not. And we want to make sure that if everybody's body is different, the interactions with these devices are different, that these medical devices always do the right thing. We also work a lot on energy systems, but today, obviously, we're going to talk about autonomous vehicles. And but no matter what topic we work on, we always have the same question that we're asking is, how do we provide the safety and performance guarantees for closed loop life critical systems? And this is a very challenging topic with autonomous vehicles. So even though we spent over 10 years working on autonomous vehicles like passenger vehicles, the problem was too wide. And there was, that if you were to able to test and validate the system in certain scenarios, what about other scenarios? What about other environmental conditions? And so that brought us to this world of autonomous racing, where the scope of the problem is very focused. And so in today's talk, I'm going to focus on 4 specific themes and where we asked 4 specific questions, and I'll describe to you the research regarding each of these specific themes, right? So when you are driving on the road, especially around the DC area, it's very difficult to know, like, are the people around you cooperative? Are they, or are they very adversarial? Are they going to let you pass or let you overtake or not? So in autonomous racing, this gets pushed to the extreme. And here, you have to basically know how to dynamically balance safety and assertiveness. So we asked this question that, in this racing context, how do we generate the most competitive agents who can dynamically balance safety and assertiveness? You crash, you're out of the race, you're too conservative, you're not going to win, and that's not even a career choice, you're out of the race, right? No point racing then. You're racing to win, but you have to continuously balance the safety and assertiveness. The next question we ask is that, well, we are racing, so we got to have the best vehicle. So how do we build the most efficient autonomous car? And this is going from, the mechanical design of the system to the perception, planning, control, the entire stack for a given racetrack. And then how do you actually improve on that design and have reusable core autonomy components that you can then transfer to different kind of racetracks or different environments. And so we look at, like, what kind of optimization happens under the hood over there. The next thing that we'll look at is, well, in this racing, for example, many companies are now investing, millions of dollars, and there are like, for example, there's the India autonomous racing where they have invested, where each car costs about $350,000, and they want to race head to head now. In fact, the race is on today in the Las Vegas CES. But what happened in the tryouts, just in simulation, was that 12 out of 16 teams crashed within the first minute of the racing. And so how do you actually do this? How do you basically, you want to stress test now, the planning and control algorithms in, with these very interactive adversarial agents. You make a move, the other agent's going to make a counter move, and so on, but you do not know how these other agents are going to go. So how do we build ways to efficiently test these, to see that, we're not going to crash no matter what the other agent kind of does along different parts of the track? And then we go up one more level to say, well, okay, racing is a very exciting area and there are many questions we can ask in it. But just like, we are kind of coming up with really good designs of race cars, the same thing we want to do for drones or for underwater autonomous, submarines and many different kind of cyber physical systems. So instead of manually coming up with these designs from scratch, just using a library of components, how can we use, AI for code design of model-based design of CPS? So, or in another way, we can say that, look, as a company like Boeing or Siemens or Bosch, they have many prior designs of generators, of windmills, of diesel engines. How can we combine, like, use these previous designs in an automatic way, but to autocomplete for new designs with new requirements, right? So I have previous designs, but now I want to make a new product. How can I now build have a model-based design tool chain, which is largely automated, but is mining previous designs and incorporating the new requirements so that I have a new product, or at least if I give it a partially completed product, like an 80% completed design, can it autocomplete to 100% with an 80% probability of success, right? So this is called the AI code designers for model-based design. So, and then the general theme is that over the years, this slide is not long enough. It goes to 2021 and so on. But over the years, a lot of students have gotten involved in autonomous racing, not just at Penn, but in over 60 different universities across the world. We have competitions. In fact, this year we'll have competitions in ICRA and IROS and CPS Week. And they have gone on to really get onto their dream careers, like in Tesla, NVIDIA, Rivian, and so on. And there's even one guy who's a YouTube star on the top right over here. I don't take any credit for his success, but he has over 8 million subscribers. And so the question more is not about here's a guy who's coming to talk about his research, is about how you can get involved, because we build a lot of open source systems, platforms, where you can actually do this racing. You don't need a $350,000 car to do that. It would be nice to do that, but before that, you can crash our smaller cars, right? So let's get started, and please feel free to ask any questions with, so we'll get started with the theme one, that is that when we are in this very adversarial setting, how do we generate the most competitive agents who can dynamically balance safety and assertiveness? And this is based on work done by my former student, Matthew O'Kelly, and my current students, Billy Zeng, along with collaborators from Stanford and MIT, and was presented at ICML in 2020. And essentially, this work over here led to also like some of the following work between Aman and Matthew, who were the two first among the first authors over here. They had a startup company that looked at how do you find unsafe driving conditions in your perception planning control stack efficiently as a startup company, and then that startup was bought out by Waymo. So they both are independently wealthy and Waymo employees, and happy for them. So essentially, if you see, as we are, for us, driving and merging onto like a highway, like in the top right corner over here, it's pretty mundane task, right? I mean, you gradually try to nudge in and get across. But for a current AV technology, it still struggles with this very non-cooperative scenarios, that this vehicle is trying to make a merge here, and this truck is not letting it in. There's no gap, and will it eventually merge? And here you want to basically do this, you want to maximize performance, but you want to negotiate this merge without any hesitation or delay and maintain safety. If you're too aggressive as an AV, then you might cause a crash like that, right? So the AV has to dynamically try to figure out how assertive it should be. And that's very difficult to figure out because it's based on, the psychology of drivers, right? I mean, in Philly or in DC, drivers are pretty aggressive compared to, say, maybe Seattle, or I don't know, I come from Bangalore, drivers are crazy over there. But if you live there, you know how they work, and then you know how to continue. So the issue with, civilian driving is that we don't know. I mean, we can say, yeah, the safety goal is very clear. Don't crash, don't get into a near accident. But the performance goal is not very clear. If I were to drive down to, UMD and I came like 5 minutes later for lunch with Yancy, then he'll be like, no problem, but at least you're alive. I mean, nobody says at least you're alive when you come driving down. But it's a kind of that kind of performance goal is very loose. So that's why we focus in racing, where the performance goal is very, very precise and explicit. So here, I think it's there's two high-speed racing cars over here. I think it's Alonso and Vettel. And you can see they're very expensive cars going at over 200 kilometers per hour, coming very close to each other. And they don't know exactly how the other driver is going to go. And they basically have to win the race now. So, and so they have a very clear criteria, both for safety and for performance, where in real world driving, we don't have that very explicit criteria for performance. That's why we started focusing on racing. So there are three sort of big differences too, right? Crashing in Formula racing is very expensive and dangerous because you're driving at over 200 kilometers per hour. The sensors that we use, LiDARs, cameras, IMUs, whatnot, those sensor observations, they don't capture the intention of the opponent driver, and we can't capture the driver's behavior explicitly like that, right? So we have to have some way to capture this more abstract, what is the driving policy of the other driver? And you could say, okay, fine, why don't we learn from previous races? We just watched many races of, Vettel and Alonso, and then we figure out that. But the thing is that the cars are secret, the race strategies for the next race are all secret. So we actually are in a very small data regime over here. And so as we start to look at this problem, we can start with a classic like reinforcement learning formulation where we have to minimize the expected cost of a set of actions over some time, right? But the problem here is that we are dealing with there's a lot of uncertainty in how the other agents behave. And so therefore we have to convert this into a mini max problem where over over this uncertainty set P, where we basically have state transition probabilities PSA and essentially, we are trying to build models that can parameterize this uncertainty space P in terms of a POM-DP. And so if we did not have this uncertainty, then, we do not need that max over there, right? So essentially now, given this, kind of formulation, which is quite general at this point, we want to learn a useful parameterization for P, and how do we really think other drivers are, and think of them, as their continuous movement of a steering angle or a next throttle position is very difficult to capture in a model where we want to sort of think of their behavior more abstractly and more descriptively in terms of their driving policy as how they would deal with any scenario, right? So we start doing this first with in an offline manner where we generate a set of very competent agents who can then compete against this opponent driver, but we don't know what this opponent driver is going to be like, and we have no idea of what their racing strategy is because it's secret. So we then have only ourselves to start with, and we use this self-play essentially to learn this and basically generate not only competent drivers but also a diverse set of opponent drivers, right? So then once we have this offline stage, when we are ready to race and we go into a head-to-head race with another driver which we have never raced with before, we basically have to use the robust planning, and this is working from this belief space of knowing, of getting an expectation of what this type of driver is who I'm racing against over a set of policies that I know from my population synthesis, right? So from my self-play, and try to figure this driver out as a mixture of the type of drivers that I have trained before, and try to minimize my uncertainty of what the other driver is going to be, and basically then plan a maneuver. So let's take a look at how this setup would be like over here, right? So the offline portion of is done in this policy parameterization, where we have two parts. We have a goal generator, and essentially that's this red vehicle over here, and it is generating a set of goals that it feels is a good set of goals, knowing that there is an opponent present over there. And then there is a goal evaluator. And so essentially we want to learn what are good set of goals as we are driving in the presence of opponents. And then we need a goal evaluator, basically, that is then identifying what is the best cost-based trajectory to take given the prediction of the other vehicle that we have, right? So once we have this sort of this framework set up, we then essentially have a search algorithm, and this is a highly scalable population-based MCMC solution, which is essentially going through this self-play and iteratively in parallel running many sort of baths of competitors with different temperatures and coming up with the most competitive agents over here. And so by the end of this search algorithm for good driving policies, we come up with basically the best set of candidate drivers, and say we have 20 or 100 such good candidate drivers at the end. And where these drivers, if you see in the top right over here, they have both diversity in how they actually drive. They're not always picking just one racing line to go around the track. They have many different ways to go around it, but they are still competitive in the sense that they finish, their lap time is very comparable. And they also have diversity in maneuvering around opponents. They're not always taking the inside track. They have a variety of ways in which they're going to sort of deal with an opponent. And so essentially we have picked these elite members from our self-play in the offline population synthesis portion. And then as we come into now the online section over here, we first sort of now are selecting a set of goals in the presence of the opponent. But here we are sort of, each agent is now, maintaining a particular belief vector WT of the opponent's pattern, but over this learned prototype behaviors, right? And essentially we want to select among these learned driving policies, what is the mix that this driver will represent? And then, and the more we can observe this agent, this opponent agent, the better, we get at understanding its driving policy. And then we want to parameterize this ambiguity set, P, as the ball around this belief, because we still have uncertainty as to this driver. It's not going to perfectly fit one of our, preset drivers that we had searched for, like that, right? So suppose we had like a library now, of say 3 opponents, 1 opponent, 1, 2, and 3. So for a given state, we can write the robust, performance objective T with respect to a prototype opponent 1 as a receding horizon cost, right? And the cost basically captures aspects of how close the agent is to another, how much progress it's made around the track, and so on, right? So what we see is with opponent 1, our expectation is that it will follow this trajectory, and we find this minimum cost trajectory to take around that. And then with opponent 2, it says, okay, well, it's actually going to take a slightly different trajectory, and we have a certain minimum cost trajectory that we would take along with that. And similarly with opponent model 3, this is our prediction of what the other agent is going to be. And so as we start to drive, we basically have this weighted, opponent model that is a mix of these 3 opponent models. And but it's not just a point prediction over here, because we don't know, which opponent is. So our belief state has an estimate of the probability of each. And so in classic versions of belief space planning, we would simply minimize the expected cost over motion planning goal samples. But in our work, instead of minimizing the worst case cost, we consider a ball around, these opponent model probabilities. And so that maintains this robust, trajectory cost, so that we can plan around that. So we repeat this basically for a motion planning goal for every part of our horizon for every opponent, and select the goal with the lowest robust cost. So for example, if there are, we would have 100 possible motion planning goals, we would then have to, for 10 possible opponents, we have to compute this 1,000 computations receding horizon cost just to set up the problem. And so here we can see that as we now start to update our belief vector, so initially we have a balance of selecting from many offline models. We are now, as we start to drive and observe the vehicle in just a few snapshots, we start to get now a weighted observation in our belief space. And so essentially, instead we just modify the adversarial bandit setting and the classic EXP3 algorithm to consider multiple plays, right, which we can evaluate in parallel. And this gives us a more confidence and a smaller uncertainty ball, essentially, for how our opponent is going to behave over here in the future, right? So essentially, the first, simple hypothesis that we had was, to see that, well, by increasing the robustness, right? That means for very uncertain opponents that or uncertain behaviors of opponents, with increased robustness, with a larger size robustness ball, are we safer, right? And we see, if we look at the time to collision values or TTC values, which is essentially saying that when we are getting very close and at very fast speeds to an opponent, and we are almost going to crash into them, so in this less than 5-second regime, that as we basically increase our robustness ball size, we see that our TTC value goes down. That means we're getting safer, and we are less often in this very unsafe regime over here. So that does, conclude the first simple hypothesis that, with increased robustness, you get increased safety. But the problem then is that, by what we really want to figure out is that by actively identifying the opponent's strategy as we race them through the course of the game, can we regain some performance, because by being more conservative here, we see that our win rate with a larger robustness basically drops from 60% to 50%. And we don't want to sacrifice that win rate. So the question is, can we regain this performance of aggressive strategies without this downside of compromised safety? So with an online adaptation, we see that now that we can maintain our win rate to around 58, 59% throughout the race. And we do this basically, and with this adaptive win rate strategy, we do this because when we're very uncertain, then we drive quite conservatively. But as we basically learn about the behavior of the opponent, then we are able to drive much more aggressively over there, right? So, and so this maintains this high win rate throughout. And with all the work we do, no matter what the theory is, we want to see this theory tested out. And so we use our Formula 110th, F110th racing cars to test this out, and implemented this strategy, and could see that this strategy works in real time on a Jetson computer on board. So there's just the computation is done only on board the vehicle. There's no external laptop running any computation online. And but as we go through this, the research questions that we still have, and that that we're open to collaboration on, is how do we approach the same problem, considering out of distribution agents that are not part of our offline, population generation set? Or is there a way to address this problem without using prototype opponents in that manner? So this brings us now to the next theme, which is on how do we build the most efficient autonomous race cars. And so the main questions over here is that we want to now optimize across hardware, software, mechanical, perception, planning, control, and how do we do this multi-domain optimization in a manner that's very efficient. And so this work is captured in this paper that we had called Tuner Car in ICRA 2020. And Tuner Car is basically this car that is like getting auto-tuned for whichever race it's going to, right? And so essentially the whole issue started with, we have many autonomous racing competitions as part of our F110 challenges every year. And I'll talk briefly about that if we have time at the end. And essentially every time the teams come there, they spend like hours and hours just manually tuning the car. And so we were like, how can we build a system that can automatically tune the car? So as it is driving, if we had different knobs for the vehicle mass, length, width, center of gravity, cornering stiffness, path planner, and controllers, and we automatically tweak them so that they initially start with very conservative drives, say of a lap time of 25 seconds. And then we tweak these parameters so that it becomes faster and faster till you get the fastest vehicle over there that's also able to do some kind of drifting as it goes. So it's operating at its limits now. And so what the question really is that, look, cars are going to change, the environment is going to change, but our vehicle planning and control stack is the same, but it has to be kind of automatically tuned. So how do we, this whole work was motivated by the desire to create this safe and reusable core autonomy that's in the center over here, agnostic of the environment or the vehicles. And so racing obviously provides this competitive environment where the clear measure is, do you win the race? What is your, minimum lap time? And any kind of suboptimal configuration is severely punished in the race. So as we have different designs, we want to basically optimize this vehicle for this race using this core autonomy stack. And then coming to our, physical vehicles for whichever race, right, we are racing in next. And so the mathematical, form over here of this is basically to minimize this objective function over the search space of, over 500 different parameters from mechanical to planning to control. And we map that into our n dimension, but we want to basically map that to a real number that says, okay, is this the most performant vehicle? And so essentially the way we do this is by using, gradient-free optimizations, because our problem is, non-convex, non-differentiable. And so we use these kind of population-based and evolutionary-based algorithms to search through this very large parametric space. And essentially, this then generates a set of candidate systems instances which we can evaluate in our simulation-based software. And as we evaluate these runs, we can then see which ones crash, which ones perform well, and this progresses through till we validate each of these within our simulation environment, but also in the physical environment itself. So the first set of results were in sort of comparing these different optimization approaches, and where for each of these racing candidates. And so as a baseline, we show all the optimizers were able to beat the simple random search given the same computational budget for that, right? So in purple, we see the 1+1 is able to lower the objective for the first few iterations, but then stabilizes, to relatively less performant ones. In orange and green, we see two differential evolution variants that find similar lap times. And then in red, there's a particle swarm optimization that finds a slightly better lap time. And lastly, in blue, that's right at the bottom, because we want to go for the lowest lap time over here, the covariance matrix adaptation finds the lap time that converges on a very good solution, because it's able to efficiently balance this exploration versus exploitation, versus other solutions are mainly picking from the earlier candidate solutions and not going very far out in terms of the exploration. And so CMA worked out very well in this sort of system, right? So we also want to look at, how sensitive the solutions are to any kind of perturbation to that parametric value. And we roughly break this parametric space into 3 subspaces for controls, decision in terms of overtaking, like in the behavioral planner, and the physical design of the system. So we run 100 rollouts with Gaussian noises with increasing variance added to the solution, to the CMA solution. And we see that the graph, in the race car is still able to have successful rollouts for at least half the time when the variance of the noise is lower than 10 to the -2 over here. And then there's a steep drop off after that, where it starts to crash a lot after that point. And we also see the decision parameters that have the biggest, impact to the overall, performance of the vehicle. So these two curves almost match each other in terms of the decision and the overall performance. So that just gives an idea of that. So one of the interesting, results that we discovered through this automatic tuning of the vehicle was in the way the system found the best solution to race, this Austria track. And so the graph shows the trajectory of a race car that took compared to the ones, from other more traditional approaches. And so the graph on the left, we show the comparison for the slip angles on the z-axis over here. And that's basically how much the vehicle is skidding. So the X and Y positions are basically the same as this 2D track over here. So we see that, the vehicle is actually slipping and basically drifting quite a lot in the optimized, race line solution that we have over here. And it's quite different. So if we zoom in to just say this turn where there's a lot of slipping, we see that a traditional race line, is much more conservative, where the car coming into the turn is braking. But here the car barely brakes. It goes in actually a very high speed and gets to a slip angle of almost 80 degrees. And it's basically just drifting all the way through and then zooming out after that. And it beats the, any kind of conservative race line. Obviously, this is very sensitive to the ground, and we see that even with our results when we actually race the vehicle and we implement this over here, right? So that's Billy, my student, and this car is basically racing around this virtual line that it has been optimized for this race line over here. And we want to see what the sim to real gap is. And so this was demoed at NeurIPS and published in PMLR 2021. And there are differences because the car is on a very slippery surface over here. It hits this gutter at this turn. and then gets onto a carpet. So there's a lot of changes in the friction, but that's what this kind of experiments give us feedback to as to how sensitive our results are overall, right? So, sorry. Yeah, and then we ran other experiments, in corridors with our F110 car, and you can see that too. Yeah, so essentially we are interested in learning like these dynamical models as the physical system, the environment, and the sensors change, go to different tracks. But now our current research is focused on how do we explore this performance tuning for multi-agent scenarios when you're racing, with more than one opponent in place, right? And then investigating the sim to real gap is always an ongoing effort. So coming to theme 3 now, as I mentioned that, in this Indy autonomous racing, just in the simulation-based head-to-head race, 12 out of 16 opponents basically crashed into each other. And you might say, oh, that's because, it could be problems with perception. In the simulation-based space, they were given ground truth-based perception. So there was not a perception issue. It was mostly to do with planning and control. And so our challenge now was, how do we explore, different ways for stressing out this? So how can we evaluate path planners and controllers, for autonomous vehicles regarding their performance? What are good performance metrics? Are they just following the line? Are they not crashing? Are they the number of overtakes a vehicle does? What are these metrics? And essentially we wanted to speed up this search for when the vehicle crashes, why it crashes, and under what conditions it's crashing, so that then we can explore and make our planner and controller more robust, right? And we are also sort of interested in this kind of coupling between planners and controllers. So which ones work well together, and so to do this, we basically had to develop an environment that was simulation-based environment that was fast and deterministic, that would capture all the vehicle dynamics over here in a two-track manner, more richer bicycle vehicle models. And then we had to come up with a good search strategy, right? And the question is, what are you searching for? A better algorithm for parametric search for your planner and controller, or searching for the submitted agents that come into our races? Is there bad vehicle behavior? Or which are the critical scenarios for a particular racetrack? So essentially, we focused on creating this intra-scenario test generation between two vehicles racing head-to-head, so that we could search for when they crash, and essentially we are searching for when these tests fail. And the failing basically maps out these, and so for as we are progressing and testing out these head-to-head vehicles racing, we are perturbing the adversarial agent at every time step to test under which perturbation will it cause our ego vehicle to crash into it, given a fixed racing strategy and a planner and a controller. And so we are interested both in maximizing the number of failing tests and to explore the variety of failures, right? So we created this deterministic autonomous F110 gym environment, which interfaces with OpenAI Gym to allow for large, very scalable testing along different F110 tracks. Like this is the Austrian track over here, and then we ran these with RRT based search strategy for these two vehicles driving head to head and perturbing the adversarial agent. And the objective space efficiently was searching for these collision based scenarios. And in order to do that, once we captured all these crashes, we could map them onto the track. And so say in this track, there's a start over here after the first turn where there is a cluster, then we found many clusters of crashes along the straight. And you say, well, why are there crashes along the straight? You'd expect crashes more to be along turns, especially around hairpin and chicanes. So this allows us to go and analyze, why crashes are happening over here. And we also have a lot of crashes as we progress through the track. And in order to do this, we could compare many different path planners like the disparity extender planner, the Freynet planner, graph planners, lane switchers with pure pursuit, so that when it sees an obstacle, then it just switches to a predetermined, pure pursuit path along a next virtual lane. And then obstacle avoidance with gap follower planners. So different planners were taken into consideration and to evaluate these crashes and clusters of these crashes. And so here's an example of this vehicle racing head to head, this purple vehicle trying to overtake this other agent, and see when it has a successful overtake, then it basically progresses more to the right over here. And it's right now looking at crashes along this curve. And the further it goes along this curve on the left side over here, it's basically progressing towards, but whenever it hits a crash, you see an X over here. And so essentially we are perturbing now and redoing the same turn, but with different initializations, and searching for under what perturbation of the adversarial agent is this ego agent going to crash. And then we can analyze why that crash is happening. And so we could then, now obviously we've done that for one track, and we could analyze the crashes all along all these different sections of these tracks to get much more insight into, what is affecting, how the path planners' decisions in terms of overtaking affect its crash rate. And so next we would want to sort of get more insight into the coupling between, the controller and the path planner. We have 5 different path planners here, 4 different controllers. We still have to analyze, how these different controllers from in terms of LQR, MPC affect the behavior of the system. And then, integrate more metrics in evaluating the vehicle performance in terms of number of overtakes. And then combine this, with the tuner car approach that designs the vehicle and also improves on the planner and controller parameters to come up with a much more competent agent. So another project that we have, and this is the last theme over here, is one level up. So I'm going to take a step back and say, okay, so far we are trying to design these race cars, make them safer, make them more competent, balance safety and performance. But now we are part of a large DARPA project on AI co-designers for model-based design systems. But they're saying, okay, let's mine previous designs to come up with, or autocomplete new designs with these new requirements. And so say you graduate and join a company to design, say, drones. Like one of my students joined Skydio. And so Skydio has a couple of models that they have designed before. It's like I think it was an 80% company that got funded more than 500 million. And then in the 3 months between him getting an offer and joining, the company doubled to like 220 people or something like that. But they are a company on the rise. They have a couple of candidate designs, couple of products out there, and they want to design new products. Like that, right? So if you're an engineer starting in a company like that, you'll say, okay, how do I design a drone? Let me talk to my colleagues. Let me see what previous designs they have, what kind of CAD models they have, what kind of drawings they have, what kind of specification and software stacks do they have, and then use those as components to create a new design. And so here the question is, is it possible to create generative models that can synthesize, these designs, but being informed by previous designs, right? So, and so we have many different research questions, but I'll just focus on just the design creation, not about how we synthesize, requirements on the input side. So, and this is a very high dimensional space where, if your boss would be like, okay, let's design a new drone for this new kind of mission type. Say all the previous drones were just, doing monitoring and tracking and surveillance. Now we need a pursuit avoid drone that can work with another drone. So it needs some more agility, more networking capability. And so this is a very high dimensional space as, mass, size, performance, safety. And then you can come up with a really new drone design, but it would cost like, $10,000 over a budget. And they say, no, it has to be below this cost, like that, right? So how do you capture that too? So most of these designs are like with experience based. You would start with like MATLAB and then go through some CAD pipeline to do this design, but they don't scale for, for complex CPS systems. So essentially what we do now is we basically mine previous designs and we treat them as design corporas or seed designs, and we capture them in a knowledge graph. So like say the batteries, the chassis, the motor drive, the motors, the fins, and so on are all captured in relations to each other. And they have constraints related to them that are also captured in the knowledge graph, and the performance of the whole of these candidate designs is captured there. And so essentially what we have to do then is to explore this constrained design space to generate new designs. And this project is in the early stages, in the first year of a 4-year pipeline, and where we have done the parametric exploration of the design space, and now we are moving to the architectural exploration to synthesize new designs. And as we come up with candidate new designs, then that's when we can then iterate through the system and improve on these designs. And this is basically a co-designer. That means it involves, as we come up with candidate designs, or we want to have certain constraints specified, we have the human come in and dictate, which are good designs, which should be eliminated out of the search space. So there has to be an interface to the human side too. So there was a hackathon about 2 months ago where we were given 3 manually constructed like hex rotors and H rotors, which have fins and rotors as C designs. And we had to come up with new designs that were using, I'll just call it AI based. I don't like the word AI based, but it's an AI based design. So it was generated designs that use like a graph VAE approach to mine the previous designs. And but they have to pass different benchmarks, right? So this first benchmark, which just shows this line, was to show an endurance benchmark that see how far can this drone fly. And we were competing with other teams from like MIT and Stanford and other universities, and so essentially it's an endurance to see can it go over 2.5 kilometers. Then there was a control trajectory design benchmark to see whether it can actually go in a circle, and it was penalized if it went out of the circle, right? And then there were like, could it hover to a certain height, and how can it go higher than that height for a certain duration of time? So that's a different kind of endurance. And then putting it all together, they had to go along a track, and then you wanted to see how fast it could go along this track, kind of like our racing thing, but with a drone over here. So these benchmarks were kind of tests that these AI-based designs had to come up with, right? So for each benchmark, obviously the AI-based system came up with different results. For like, say, going for endurance, it basically put on a hex rotor so that it could move through but it required more batteries for that, right? So this is nothing influenced, there's no human actually interplay in these designs. The interesting design was like this design number 2, where it had to go around a circle. Since it's going around a circle in only one direction, it found that it had to put less effort on the inside rotor. And so basically this inside rotor is smaller than the other 3. And so it actually optimized just for going around the circle in one direction. If we made obviously the benchmark to go around the circle in the other direction, it would have a different, it's still invariant, but that's an interesting choice. This design 4, we didn't even believe it could fly, but it actually flew and gave us a very good, score. And the scores were basically on to see how close we could get to the maximum possible score for these benchmarks, right? And as we go forward, it's about how do we capture and extract, these relationships between these components from prior designs and basically build this entire automated pipeline, right? So I have about 5 minutes left. I just want to wrap up here. So autonomous racing is all about, racing at the edge of performance, where you have to detect the vehicle's limits, make these decisions at a very high speed, and be able to handle that, balance safety, be able to stress test the vehicle, and also be able to come up with optimized vehicle designs for the particular track and for the particular competition that you're working on. But most of all, the important thing is that it explicitly defines the criteria for safety and for performance, unlike civilian driving. And unlike civilian driving, all our opponents are adversarial, right? So we are working in the worst possible conditions to basically make the safest possible vehicle. So in order to do this, we have many activities with our F110 systems where we organize workshops in autonomous racing, and we have competitions. We had competition in IROS. We'll have one in the Philadelphia ICRA in May. So please participate. That information will be on the F110's webpage. And last but not the least, the questions are like, how can you get involved? And I think these slides are just muted out, but I'll just cover a few. So we designed these 110 scale autonomous racing cars, and that have GPUs on board, lidars, cameras, and we can send a car to UMD for free to get started. And many universities are teaching this as a course to go from mechanical to putting all the sensors together. Now these cars are ready now. You don't have to worry about putting them together. You can already do your research or basically race for a competition with these. There is a F110's gym and the LG SVL simulator, which has our it simulates the full the same software stack in 2D and 3D. So you can actually utilize all of that before even touching the car. And we help the community build, code, and race these vehicles to go from simple obstacle avoidance gap finding algorithms to SLAM runs perfectly well on this platform. To go to more complex algorithms like RRT star runs perfectly well on this platform. You can see it for real out of the box. To go from simple PID control to MPC, full runs on this track. You can see in our past races how vehicles are competing against each other using MPC. And so we've designed a course that we teach every semester on autonomous racing that takes you from the basics of ROS all the way to perception, planning, control, learning, vision. And there are no exams in this course. There are just competitive races that are part of it. There are obviously 8 very rigorous labs, but the students have a lot of fun. And then the students do a lot of research projects at the end of the semester in a variety of areas that they're interested in using these vehicles and the simulation environments. There are many competitions, and over the years, we've had many competitions. In 2022, we'll have 3 competitions in ICRA in May, and in the CPS week, also in May, and then in IROS later in the year. And these are in-person competitions, of course, modulo how Corona treats us, but it's going to be in Philadelphia in May. So it's very easy for UMD students to come and compete. There are many, many universities, including folks in UMD that have supported this and are participating in F110. And this is the website. So I'll be happy to take any questions. Thank you.
Thank you very much, Rahul. That was a wonderful talk. I really enjoyed it. Do we have any questions from the audience? You can either raise your hand and I can unmute you so you can ask directly, or you can post it in the Q&A feature. Dinesh, please go ahead.
Hi, Yancy, can you hear me?
Yes.
Yeah.
Really nice talk. Thank you. So you addressed a lot of very important issues. I'm just trying to get a sense of, you're focusing on this autonomous racing and the bigger problem of autonomous driving. You mentioned about Bangalore conditions. So in autonomous driving, there's a big holy grail about urban driving, urban challenges, and they talk about traffic lights, bicyclists, pedestrians, VRUs. Do you see similar problem, or there are quite a few differences in your domain and the broader autonomous driving?
That's a great point, Dinesh, and I'm quite familiar with your work in the very cluttered driving environments. I think to some extent the move to the racing was to slightly uncluttered environments, or drastically uncluttered environments, I should say, where and so far the work that we have done has mostly been on planning and control. And now, I think it would be very useful to move to bring in the perception part, and actually FITENTH just recently got is a native part of the LG SVL simulator, so far we've just been using LiDAR based navigation on the real car, and in our most of our research we've just been assuming that the perception is based on ground truth, right? Which is a big I think that's really where 99% of the challenges are with autonomous driving in general. And I think that would be something to sort of work on together, and that's something that now we are ready to do with the new simulation environment and the new sensor setup we have with these systems. So far we've just focused on the challenge with racing has largely been with the interplay between the planning and controllers and how to do these overtakes in an aggressive but safe manner. And so we've discounted kind of knowing the pose of the other vehicles to just focus on that part.
Thanks.
Great, thank you so much. We have time for one more question from the audience. And so while we wait around for that, I want to take a moment again to thank you for coming to this or presenting for us in the robotics seminar series. This is actually the last talk for the semester, and so it was we're very happy to have had a chance to have you kind of close us out. And so with that, I also want to thank the audience for coming. I'm going to stop the recording, and then we can stick around and answer any more questions.
Thank you.